Hello, and welcome to Differential Equations. This is Lecture 10, the Wronskian. So last time, we talked about linear ordinary differential equations and the principle of superposition. Right, the principle of superposition says that if y1 of t through ym of t are solutions of a linear homogeneous ordinary differential equation, and you pick any constants, then the linear combination y of t is c1 y1 t plus dot 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 up to cm ym of t is also a solution. Okay, this time we want to know when is the general solution of this equation a linear combination of the set y1 through ym of solutions. Okay, so the first thing to say is that if you're going to pick a set of solutions and then write every solution as a linear combination of them, then we want to be efficient. In our set S of solutions. Right, let me go ahead and say y1 of t to ym of t. So what I mean by efficient, so if one solution, if one of these solutions can be written as a linear combination of the other ones, and we don't want to include it, right? Because including it doesn't add any information to what we already have, right? Doesn't give us any more solutions than we would have without it. Okay, a set is called linearly dependent if one element is a linear combination of the others. Right? More formally, let's write down a definition. A set of functions is linearly independent. If whenever you have a linear combination of constants times these functions and you get 0, and importantly, when we write a linear combination like this equal to 0, we mean the function 0, right? So it's equal to 0 for all t. If that implies that all of the constants Ci are equal to 0. A set of functions is linearly dependent when it is not linearly independent. Right? So another way of saying that is if there is a linear combination equal to 0. Again, this is the function 0, not just the number 0, where the coefficients are not all equal to 0. If your set has at least 2 elements, then that's the same as what we wrote up here. Linearly dependent means that one element is a linear combination of the others. Okay, so for example, if S contains a single function, then S is linearly dependent if y1 of t is equal to 0 for all t, right? So if the function you have, the only function you have is the 0 function, then you have a linearly dependent set and linearly independent otherwise. If S contains 2 functions, then S is linearly dependent if one of the functions is a constant multiple of the other, and is linearly independent otherwise. As a very simple exercise, check these statements I've just made using the definition. Let's keep going with examples. The set that has the functions 1t and t squared is linearly independent since if you have a times 1 plus b times t plus c times t squared, and this is equal to 0 for all t, right? Well, you have a polynomial of degree 2, and it's equal to 0 for all t, then the polynomial itself has to be 0. Right? On the other hand, the set S that has, say, 1 plus t, 1 minus t, and t, right, is linearly dependent, right? Notice that no one of these functions is a multiple of another one, right? So it's not the case that one function is a multiple of another one. Nevertheless, these three functions taken together are linearly dependent, since we could do, say, 1/2 times 1 plus t minus 1/2 times 1 minus t, right? Minus, or let's say plus minus 1 times t, and we get 0. And these coefficients are not all 0. Okay, let's do one more example because we used it last time. The set with the functions e to the 2t and e to the minus 2t is linearly independent, since if you have a times e to the 2t plus b e to the minus 2t equal to 0 for all t, then a and b have to be 0. All right, how do we know? Well, many ways you could check. For example, if you plug in t equal to 0, we would get a plus b equal to 0. And at t equal to 1, we would get a e squared plus b e to the minus 2 equal to 0. Right, but this would tell us a is equal to minus b. And this would tell us a, which is the same as minus b. So a e squared minus e to the minus 2 is equal to 0. But that tells us a is equal to 0, and plug that back here, we get b equal to 0. We know that e squared is not the same as e to the minus 2 because, for example, this is greater than 1 and this is less than 1. So that set is linearly independent. Okay, so coming back to our general purpose, we're given a linear ordinary differential equation. We have a set of solutions, and we want every solution to be a linear combination of elements of this set. We want our set S of solutions to be linearly independent, right? Just so that it's an efficient description of the solutions. What else? Okay. Well, we know that there is a unique solution to the initial value problem where you have the nth derivative of y with respect to t plus the terms that use the lower order derivatives equal to 0, and then you have y of some point is y naught up to the n minus 1th derivative at that point is y naught n minus 1. So this initial value problem, the existence and uniqueness theorem tells us that as long as these functions are continuous, this system has a unique solution. So what we need from our set S of solutions what we need from it in order to know that we're getting the general solution to this equation is that for any choice of constants, y naught up to y naught n minus 1, there should be a unique set of constants, C1 through Cm, such that when you take the linear combination with coefficients C1 through Cm, this satisfies the initial conditions. Y of t naught is y naught, y prime at t naught should be y naught prime, up to y n minus 1 derivatives at t naught should be y naught n minus 1. Okay, so that's what we want from our set of solutions. We decided we wanted to be linearly independent just for efficiency's sake, and what we need is this. So first notice that we have n equations, right? Here are equations. And m unknowns, right? Here are our unknowns. So for uniqueness, we should have n equal to m. Okay, so let's say that we have n solutions for the nth order linear ODE. Then the system we want to solve is, okay, so we want y of t naught should be y naught. We want y prime of t naught should be the constant y naught prime. Dot, 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 we want the n minus 1th derivative at t naught should be the constant y naught n minus 1. Okay, if we plug in that our function y is given by this, then what this first equation says is C1 y1 of t naught plus dot, dot, dot up to Cm ym of t naught should be equal to y naught. And then the second equation says that C1 y1 prime of t naught plus dot, dot, dot Cm ym prime. Oh, actually, m is n, we decided. Is y naught prime. And then this last equation says C1 y1 n minus 1 derivatives at t naught plus dot dot plus Cn yn n minus 1 derivatives at t naught, all that should equal y naught n minus 1. Okay, so the system of equations we want to solve, if you write it out in terms of our functions y1 through yn, becomes this. And then if you write that system in terms of a matrix, this says that you have the coefficient matrix y1 of t naught, y2 of t naught, dot dot dot, yn of t naught, y1 prime of t naught, y2 prime of t naught, dot dot dot, yn prime of t naught, y1 n minus 1 of t naught, y2 n minus 1 t naught, yn n minus 1 t naught. We have this matrix multiplying the vector C1, C2 up to Cn, and that product should give you the constant vector y naught prime, up to yn, y naught, n minus 1. Okay, so the system we're interested in, right, if you write it out, is equal to this, and then if you write that out using matrix vector multiplication, it looks like this. Okay, so recall that a linear system of equations like this of n equations with n unknowns, right? So that means that this matrix has n rows and n columns. Right? This system has a unique solution if and only if the determinant of the coefficient matrix is not equal to 0. Right? So in order for this equation to have a unique solution, what we need is that the determinant of this coefficient matrix is not equal to 0. If the determinant is equal to 0, then there are either no solutions or multiple solutions. Okay, this determinant is important enough to get a name, right? So that's the Wronskian. Given a set S of n functions, the Wronskian, sometimes called the Wronskian determinant, of S is w of y1 up to yn. Right? Notice this is a function of t. It's the determinant of this matrix, the coefficient matrix that we had above. So you have the first row, you just put all of the functions evaluated at t, right? And then successive rows, you take derivatives until the last row, you're taking n-1 derivatives of each of the functions. So you take the determinant of that matrix. Okay, so wonderful. So let me scroll back. What we needed from S in order to know that we had the general solution to this system, right? What we needed is to be able to solve this system of equations uniquely, right? And we saw that to solve that system of equations uniquely was the same as solving this equation uniquely. And we saw that solving that equation uniquely was the same as having the determinant of the coefficient matrix not zero, right? And we've called that determinant the Wronskian. So if we put all of that together, we see that if S, right, containing the functions y1 of t to yn of t, is a set of solutions to the equation, the linear ODE homogeneous ODE, then every solution to the initial value problem where you have this same equation but now you have initial conditions specified at the point y naught, sorry, at the point t naught, then you're guaranteed that this can be, every solution can be written as a linear combination of the elements of S in a unique way if the Wronskian evaluated at the point t naught is not equal to 0. Okay? That's great. The Wronskian settles our initial question. There are a couple of important properties of the Wronskians that we should note. So first, let's call it a proposition. If the set of solutions is linearly dependent, then its Wronskian is identically 0. Right? So we talked about wanting a linearly independent set of solutions just from the point of view of efficiency, of avoiding redundancy. But on the other hand, if the Wronskian is going to be how we measure our success, then we need to have a linearly independent set if we want the Wronskian not to be 0, because when the set is linearly dependent, the Wronskian is identically 0. Okay, so the proof is very easy as long as you remember properties of the determinant of matrices. So the thing to notice is that if one of the functions is a linear combination of the others, then one of the columns in the matrix we're interested in is a linear combination of the other columns. But that causes the determinant to vanish. Okay. The second important property of the Wronskian is a theorem due to Abel, Niels Heinrich Abel. It says that if y1 of t to yn of t are solutions of the nth order linear equation with coefficient functions aj, then the Wronskian w of t satisfies the first order homogeneous equation dw dt plus an minus 1 of t w equal to 0. Okay, so the first order homogeneous linear equation with coefficient function an minus 1, so it's the same coefficient function we had up here. Okay. So the proof is not hard. It's again just properties of determinants. So let's compute the derivative of the Wronskian with respect to t, right? So this would be the same as the derivative with respect to t of the determinant of the matrix that has first row given by y1 of t up to yn of t. Let's see, dot, 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 and then I'll include the next to last row. Let me give myself more space. The next to last row would be y1 n minus 2 derivatives up to yn n minus 2 derivatives. And then the last row would have n minus 1 derivatives. Okay, so that's the matrix, and we're taking the determinant. And then we're taking the derivative. Okay, so let's think about what happens when you take the derivative of this function, right? Taking the derivative, well, the determinant can be written as the sum of a big product. In this big product, you're including one term from every row and one term from every column, right? So by the Leibniz rule, when you take the derivative, you're going to have one term where you take the derivative of the first element, then plus when you take the derivative of the second element, plus when you take the derivative of the third element, and so on, right? So in terms of the determinant, you can think of that as we're going to have the determinant of this matrix when we take the derivative of the first row, plus the determinant of this matrix when we take the derivative of the second row, plus the determinant of this matrix when we take the derivative of the third row, and so on, plus the determinant of this matrix when we take the derivative of the last row. Okay, but let's think about what happens when you do that. If you take the derivative of the first row, so you're just replacing the first row with y1 prime up to yn prime, well, that's exactly what the second row is. So that determinant is 0 because you have repeated rows. And if you take the derivative of the second row, then that's replacing the second row with the third row. So because you're repeating rows, you just get 0. When you keep going, when you take the derivative of this row, you would get this row. And because you're repeating rows, that matrix has determinant equal to 0. So the only time when you get a determinant that's not automatically 0 is when this derivative hits this last row. So this derivative is the same as the determinant when nothing happens to this first row, nothing happens to this next to last row, but the final row gets replaced by the nth derivative, right? Because we took one derivative. Okay, but now let's stare at this last row, right? This first element, say, y1 is a solution of this equation. So if you take its nth derivative, what you're computing is exactly this term for y1. So you can replace it with this. You just move this to the right-hand side, right? So this is the same as the determinant of, right? Nothing happens to the first row. So you get the next to last row. And then this final row, I can replace it with minus the sum aj, j goes from 0 to n minus 1, t times the jth derivative of y1. Actually, let me denote this y j1 of t. Right, and same thing here, this final term. So again, all that happened there is that when you take the derivative with respect to t, because of the Leibniz rule, the derivative with respect to t of a determinant is the same as take the determinant when you've taken the derivative of the first row plus the determinant when you've taken the derivative of the second row plus dot 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 the determinant of the matrix when you've taken the derivative of the final row. Because you get repeated rows, except when you take the derivative of the last row, this derivative ends up just being the determinant of this matrix when you've taken the derivative of the last row. The derivative of the last row gives you nth derivatives, but these functions solve this nth order ODE. So we know what the nth derivative is. It's given by this, right? Because all of these solve this. Okay, but now, again, properties of determinants, if you have repeated rows, they don't count. They just give you determinant equal to 0. So here, when we have the first derivatives, that would repeat the first row, right? Because they would all be multiplied by minus a1 of t, right? So it's just going to be a multiple, a fixed multiple of the first row. The same thing when we look at the second derivative here, that would be a fixed multiple of the second row, right? And so on, the n minus 2th derivative would repeat this row. So the only term here that is not repeating any one of these rows is the last one. So I can replace this with the determinant of the matrix where here I just have minus a n minus 1 of t y1 n minus 1 evaluated t dot minus a n minus 1 of t y n n minus 1 of t. Okay, and then this matrix, this final row is all being multiplied by the same constant minus a n minus 1. So I could pull that out of the determinant, and I would get minus a n minus 1 of t times the determinant where you have y1 of t all the way down to y1 n minus 1 of t, and then yn n minus 1 of t, y n of t. And we recognize this determinant as being the Wronskian. So altogether, we ended up with minus a n minus 1 of t, w of t. So notice that the derivative of w with respect to t ended up being just minus a n minus 1 of t times w of t. And that's exactly the equation we wanted to show. Okay, so that's Abel's theorem. And what's important about Abel's theorem is a simple corollary. The Wronskian satisfies this linear first order ordinary differential equation. We know how to solve these, right? This you can solve by just doing separation of variables, right? This is a separable first order equation, so it's easy to solve. And what you should notice is that if the coefficient functions a1 of t to an minus 1 of t are continuous, on an interval, then the Wronskian of solutions to this equation is either identically 0 on this interval or never equal to 0 on this interval, right? And the proof is just that if you have this first order separable differential equation, right, then what you can do is write this as, let's say we go ahead and write it in differential form notation like this, right? Then by integrating both sides and taking the exponential, we see that w of t is equal to some constant times e to the minus the integral n minus 1 of t. right? And the point is that an exponential is never equal to 0. So this function, if it's equal to 0, it's because this constant is 0, and then this function is just always equal to 0. And if it's not identically equal to 0, that means this constant is not equal to 0, and then this function is not equal to 0. Okay. Wonderful. Let's just, as an example, compute the Wronskian of the set e to the 2t and e to the minus 2t. Right? So here, y1 of t is e to the 2t, y1 prime of t would be 2 e to the 2t, y2 of t is e to the minus 2t, so y2 prime of t would be minus 2 e to the minus 2t. So the Wronskian of y1, y2 would be the determinant of the matrix e to the 2t, 2 e to the 2t, e to the minus 2t, minus 2 e to the minus 2t, right? And so the determinant is just you multiply these two minus multiply these two, and so you get minus 4, right? So we see that it's not equal to 0, just as we expected. Okay, so feel free to stop watching there. I will just finish up with some historical context that you can listen to if you want, or ignore if you like. So this time I thought I would tell you about Wronski because we were studying the Wronskian. So Wronski is Joseph, and most of his, well, that's not true. The beginning of his life, he was not named Wronski at all. He was Joseph Henne. He was born in Poland in 1778, and he died in 1853. 1778. So to understand Wronski's early life, let's talk a little about Poland in the 18th century. So the end of the 18th century was a bad time for Poland. I say Poland, I should really, more correctly, I should say Polish-Lithuania monarchy, but we'll just stick with Poland. Poland had a system back then of royal elections where a king was chosen by the nobles in a free election, and they often chose foreign nobles to become king. So this meant that the king of Poland would be some Russian prince or some German noble or something like that. This was a terrible system because by the early 18th century, this meant that the Russian Tsar was effectively choosing who would become king of Poland, right? So Poland was in practice serving as a Russian puppet. Many Polish nobles resented the influence of Russia, and this led to a civil war in 1768, between 1768 and 1772. Unfortunately for Poland, this civil war meant that Poland was pretty weak when the powers that were surrounding it were pretty strong. So in 1772, Russia, Austria, and Prussia were led by strong people. Russia was led by Catherine the Great, Austria by Empress Mary Theresa, and Prussia by Frederick the Great. And so they just decided in 1772 they would seize Polish territory and divide it among themselves. This is known as the First Partition of Poland. Poland lost half of its population and a third of its territory. Okay, so Poland politically felt the need to regroup. And so they built up their strength, and like 20 years later, Poland adopted a liberal constitution in 1791. This is the second constitution in history and the first in Europe to be adopted, first written constitution in Europe to be adopted. Second in the world after the US. The US, right, the Constitutional Convention was 1788 and it was adopted in 1789. In Poland, 1791, this instituted a constitutional monarchy. And now Russia, specifically still Catherine the Great, viewed these liberal reforms as a threat to its influence. And so it allied with conservative Polish nobles and invaded Poland, leading to a second partition in 1793, again between the three powers, Prussia, Austria, and Russia, which left Poland only a small buffer state with a puppet king and Russian garrisons. Okay, so 1793, right? This is after the American Revolution, and the American Revolution had the benefit of a Polish general by the name of Tadeusz Kościuszko. He was a military engineer, but for example, he took part in the Battle of Saratoga. This was a really important battle in the American Revolution because it's the first one where the Americans achieved a significant victory, and so the French and other European powers, but especially the French, started taking the American side seriously and loaned the Americans money, which was really important. But in any case, Tadeusz Kościuszko went back to Poland after the American Revolution, and in 1794, after the second partition had happened, he led a revolt to try to take back Poland for the Poles. It did really well initially, but then they were defeated by the Russian army, and this led to the third partition of Poland in 1795, which basically ended the existence of Poland as an independent political entity until 1918, until the end of World War I. Right, so what's Wronski have to do with that? Well, Wronski was born in 1778, so he was a young man when the second partition happened, and he joined the side of Kościuszko to fight in rebellion against the Russian army. He was wounded, taken prisoner by the Russians, and then made to serve in the Russian army until 1797, when he was able to leave with the rank of lieutenant colonel. Once he left the Russian army, he went to Germany, where he studied philosophy. Then he enlisted in what are called the Polish legions in France. So what happened after Poland was partitioned for the third and final time, 1795, many Poles thought that their natural ally was revolutionary France. So they went to revolutionary France and they formed Polish legions. These were very significant in Napoleon's fights. And Napoleon ended up creating a Duchy of Warsaw in 1807, but it disappeared after he invaded Russia in 1812. And the Polish legions were disbanded then. Wronski joined the Polish legions, but he did not stick with them that long. He became a French citizen in 1800. He went to Marseille to work at an observatory there in 1803, and then he moved to Paris in 1810. And that's when he changed his name from Joseph Henne to Joseph Wronski, or sometimes Joseph Henne Wronski, or sometimes just Henne Wronski with no Joseph. He, while he was in France, worked on developing theories about the universe and its origins. He thought that he had come up with a completely new approach to science. Inspired by the Pythagoreans, he thought that everything was number and that somehow there was some mystical connection between philosophy and math. He thought that math was too rigorous, never a good sign. And he tried to apply philosophy to math, usually with really bad results. In fact, most of what Wronski claimed in math was either nonsense or incorrect. But apparently, many of his intermediate results had important applications and contained novel ideas. The Wronskian determinant, in particular, this appeared in a work in which Wronski was criticizing Lagrange, a much more important mathematician, and specifically criticizing Lagrange's use of infinite series. So Wronski was saying, no, that's not what you should be doing to understand a function. You should be using some other series. And as the coefficients of this other series, he wrote down what we call the Wronskian. Again, Lagrange was right, Wronski was wrong. So Wronski's ideas didn't really have much of an effect until like 30 years after he died. 30 years after he died, there was a Scottish mathematician called Thomas More who wrote very significant work on the theory of determinants, and then later a 4-volume history of determinants, which was very influential. And when in Moore's work on determinants, he defined the Wronskian and named it after Wronski. It's after Moore that we call it the Wronskian. So there you go. Wronski ended up dying in Paris in poverty and not highly regarded. But now he lives on in our differential equations classes through the Wronskian. We'll stop there and pick it up next time.